Start small.
Gosh,
Explosions all have one thing in common, which is rapidly produced and rapidly expanding gases. This video explores why nitrogen triiodide explodes. What is the chemistry behind the explosion? Nitrogen triiodide, or Ni3, is particularly interesting because it is so unstable, and we will explore that as well, including energy considerations that result in the explosion. Let's begin with two tendencies of nature that will help us understand the chemical reaction that occurs in the explosion. The first is that nature has a tendency to decrease potential energy in any chemical or physical process, and we will get to that in more detail momentarily. The second is that nature favors an increase in entropy. An increase in entropy is popularly described as an increase in disorder of a system. An ordered system, such as a crystal, has less entropy than a disordered system, such as a gas. An increase in entropy can also be thought of as a dispersion of the system's energy. The energy of a crystal is all in the crystal. If the crystal's components become a gas, then that energy gets spread out as gas molecules spread out. Notice in the decomposition of Ni3 here, the Ni3 begins as a solid crystalline compound, which has low entropy, and becomes two gaseous products, which have higher entropy. Entropy favors this reaction. In terms of potential energy, we need to understand that in the synthesis of Ni3, the iodine atoms are so large compared to the nitrogen atom that they don't really quite fit around the nitrogen atom, and in fact there is a great deal of repulsion between the iodine atoms. Iodine atoms are crammed into each other, but not bonded to each other. Iodine atoms are all bonded to the nitrogen atom. This type of repulsion is very important in chemistry, in particular in chemical properties. Repulsion between non-bonded atoms in a molecule happens all the time to varying degrees. Here, in Ni3, that repulsion between iodine atoms is quite large because they are so close together. This repulsion has a name. It is called steric strain or steric hindrance. The term steric relates to the three-dimensional arrangement of atoms in space. What this tells us is that Ni3 is not a very stable molecule. Those iodine atoms don't want to be there because of their mutual repulsion. That tells us why Ni3 so quickly falls apart, so easily decomposes. In fact, it decomposes at room temperature without addition of any activation energy. But that doesn't tell us why it explodes. If we want to know why it explodes, we have to understand two things. One, the speed of the decomposition, and two, the energy considerations. First, the speed of the decomposition of a mass of Ni3 is almost instantaneous because even if only one molecule of Ni3 decomposes in a big lump of Ni3, the fast-moving nitrogen product will bump into the next molecule and will set off a chain reaction of decomposition through increasing the kinetic energy of the rest of the Ni3 through conduction of kinetic energy at about 3,000 meters per second. So the Ni3 molecules all decompose in an extremely tiny time span because each molecule of Ni3 is so unstable. The speed of the decomposition is essential, as we shall see. Now we will talk about energy. An important part of this story is potential energy versus kinetic energy, which can be viewed from a physical perspective and a chemical perspective. Let's first look at the physical, and that will help us understand what the chemical perspective tells us about explosions. So in a physics class, you may think of a rock at the starting point of sitting on the ground as having zero potential energy. And here we define potential energy as the potential to do work. The rock is just sitting there. It is not doing any work. If we lift up the rock so that its distance from the Earth increases, its potential energy increases. Its potential to do work increases. We can understand this potential energy increase as a result of its distance from the Earth, because when let go, its potential energy decreases back to zero as it goes back to its original position. As it loses potential energy, the rock does work on the air by pushing it out of the way, and the rock does work on the earth by pushing on it in the collision. The earth also does work on the rock at that point, but that is another story. What we now need to consider, believe it or not, is that thing called conservation of energy. So a better way of looking at this is to look at how energy is conserved. As the rock gets closer to the earth and decreases in potential energy, it has in exact proportion an increase in kinetic energy, the energy of motion. You may think at this point that the kinetic energy has gone to zero, but of course it has not. The kinetic energy has been transferred to the earth and to the air, which is the work it has done on the earth and on the air. We have saved the law of conservation of energy. So how do we relate this to what is going on in a chemical process? Let's take a look. Potential energy in molecules also depends on position, the position of valence electrons and nuclei in atoms and molecules. And it is also the potential to do work. In terms of doing work, it is probably easiest to think of potential energy in molecules as the potential for a molecule to react. And it is through that reaction that work gets done. So high potential energy means a high potential to react. Low potential energy means low potential to react. It is the outcome of the reaction that does work on its surroundings. For the decomposition of solid Ni3, what we get is one nitrogen molecule and 3 iodine molecules, and these are gases. But to really understand why an explosion occurs, as opposed to just a decomposition, we have to look at the nitrogen molecule in particular. The nitrogen atoms are triple bonded, and that triple bond has incredibly high bond energy, 941 kilojoules per mole. You would have to add 941 kilojoules to a mole of nitrogen molecules to break a mole of those bonds. That is a large amount of energy, a very high bond energy, which tells us it has a very low potential to react. That gives nitrogen an incredibly long half-life in the atmosphere. Much of that half-life is due simply to lightning splitting nitrogen apart in a storm. By comparison, the bond energy between nitrogen and iodine in Ni3 is only 139 kilojoules per mole. Ni3 therefore has a very high potential energy, a very high potential to react. Let's move on to the significance of that large potential energy difference. It is that difference in potential energy that allows us to understand why an explosion occurs. We simply need to obey the law of conservation of energy. So what does this loss of potential energy mean for kinetic energy within the law of conservation of energy? Well, just like the rock gaining kinetic energy as it loses potential energy when falling to the earth, so it follows that as that large amount of potential energy is lost in the reaction, the kinetic energy of the nitrogen molecules produced in the reaction will be extremely high and moving away from the reaction at thousands of meters per second. Of course, we are not dealing with a single nitrogen molecule. There are many sextillions of nitrogen molecules coming out of an amount of solid Ni3 that would be visible to the human eye. Because that Ni3 decomposition happens so rapidly, all those sextillions of nitrogen molecules are produced in a very tiny time frame, and so they create a very strong pressure wave. That is the explosion. Those fast-moving gas molecules will transfer their kinetic energy through collisions to a wall or window or air or eardrum and push with great force on whatever they collide with. That is how any explosion works. That is the work done on the surroundings by this chemical reaction. For Ni3 to explode, however, the crucial requirement of a large change in potential energy is driven home even more when considering what happens in the formation of the iodine molecule, I2. Iodine molecules have a much higher potential energy than nitrogen, and so the difference in potential energy between Ni3 and iodine is not very much, far less than the potential energy change from Ni3 to nitrogen. So when the iodine forms, it has far less kinetic energy than the nitrogen, So it comes out of the reaction as a growing cloud of purple gas that does not have much energy to push on whatever it collides with, in large contrast with the high kinetic energy nitrogen. So the formation of iodine molecules would not cause an explosion. There is not enough kinetic energy. You need the high-speed gas molecules that the nitrogen molecules provide to cause that explosion. Note that nitrogen gas is never visible. So in this demo, it is not the visible iodine that we are hearing. It is those high-speed nitrogen molecules that are causing that pop. So here we come to a major point in the video, which is that the potential energy difference between the decomposing explosive compound and the resulting gaseous product has to be large enough to create very high-speed gas molecules. The molecule nitrogen has such a low potential energy that it is a component of any powerful explosive, which are called high explosives and are decompositions, such as nitroglycerin, TNT, C4, and etc. The potential energy difference between any quickly decomposing compound and nitrogen will always be large, producing high-speed nitrogen molecules. For an explosion, of course, we are talking about sextillions of gas particles. The size of any explosion is not only based on the speed of the reaction and the speed of the product, but the amount of product as well. This has been a Mad Scientist production. See ya.